Welcome to Abhi's Math e-Pathshala. Today's topic is quotient groups.
So let us recall that if we consider a group G and a normal subgroup N of G, N of G, then we can construct a group which is denoted by G slash N of left or right cosets of N in G with respect to the operation, the binary operation defined on G slash N by, suppose you are considering left cosets. So take two left cosets An and Bn, and then it will give you some another left coset Abn. And with respect to this binary operation, we have proved that G slash N forms a group with respect to this binary operation. So this group is defined as has been defined as the quotient group or factor group of G by the normal subgroup N. So given any normal subgroup of a group G, you can construct a quotient group. So this is a basic way of constructing new groups from the old ones using their normal subgroups. Okay, fine. Now uh, now it should be noted that you can write down some facts of this quotient group of G by N as, so fact 1 is that suppose G be abelian and N be a normal subgroup. Okay, of G, then one can prove that its quotient group is also abelian. Okay, okay, fine. Next one is that uh, suppose G be a finite group, right, and N be a normal subgroup. Of G. Okay, so then by means of Lagrange's theorem, you will definitely have that the index of G by N is the quotient in the division of the order of G by order of n. So then the index G colon x n is equal to this, right? But now, since n be a normal subgroup, so you can definitely have a quotient group G slash n, and definitely this index is equal to the order of the quotient group, right? Yes. So actually, if n be a normal subgroup, then the order of the quotient group equals to the order of G by order of n. So by means of Lagrange's theorem, right? Okay. Fact 3. Okay. Now let G be the group of integers. Okay. And since the group of integers is abelian, so any subgroup is normal. And the subgroups looks like, so suppose you have a subgroup n, then it looks like nz, right? Okay. Where n be a positive integer, right? Okay. So these are all the types of non-trivial subgroups of Z plus. Then, since Z plus is an abelian group, so NZ is normal. So you can definitely have a quotient group out of this normal subgroup, right? Now, how does it look like? The quotient group of Z plus by NZ. So how does it look like? So we shall have a discussion on that. So let small a belongs to Z. Okay. Then what is the left coset determined by A of n in G? That is A plus nz, right? That means it constitutes of all those elements of the form A plus nq, where q belongs to Z. Okay, right? Now, if we use division algorithm to A, and we shall divide A by n, then by division, if we use division algorithm, then there exists a q dash and r belongs to Z, such that A is going to be nq dash plus r. Now what is r? R will be from 0 less or equal to r less than or equal to n minus 1, right? So the possibilities of r are the integers from 0 to n minus 1. So that means A plus nz will take the form either of, so suppose if r is 0, then it will be A is of A will be nq dash. So that means so it is nq dash plus r plus nq, where q dash Q both are in Z, right? Okay. So that means this Q, 1 minute. So Q belongs to Z for some Q dash belongs to Z, right? So that means now taking common of n, so that means it is n Q double dash plus R, where Q double dash belongs to Z. Okay. So that means this is going to be the coset R plus nz. Okay. So A plus nz is equal to R plus nz. Now what are the values of R? Possible values of R are 0, 1 to n minus 1. So that means, so therefore, the possible distinct left cosets of nz in Z are. So whenever you are taking R equal to 0, so then it will give you nz. Whenever you are taking 1, it will be 1 plus nz. Whenever you are taking 2, it is 2 plus nz, and so on, right? Okay. Okay. So that means, so this implies the factor group of nz in Z of Z by nz is equal to, so the elements are nz plus 1 plus nz, 2 plus nz, and n minus 1 plus nz, right? So that means in terms of, so Z by nz consisting of the left cosets of this form. If you consider right coset, then you will have the corresponding right cosets. Okay, fine. So that means this group also has n elements, right? Okay, n elements. And now if you recall that for any n greater than 0, you have a finite cyclic group of order n, which is Zn, and this group comprises of the elements 0 plus, 2 plus, n minus 1 plus, right? So you are having two groups of order n. One is Zn that you have constructed earlier, and now in terms of quotient group by nz in the group Z, a z by nz. So this is again a group of n elements. So you are having two groups having same number of elements. But if you look at the groups closely, you will see that you can set up, one can define a map, phi from Z by nz to Zn by phi of R plus nz equals to R class, right? For all R equals to 0, 1, 2, n minus 1. Now later you will see that with respect to this association, this correspondence phi, we will see that actually these two groups are same. In terms of group structure, these two objects are same. Okay, although they are elements, although they are elements, are looking like different. Okay, but as a group, these two groups will be same. Okay, okay, fine. Now in this way, okay, let us take another example. Suppose, so let G be R2. That is the Euclidean plane. Okay, okay, and let O be the origin. Okay, with respect to a given coordinate system, let O be the origin. Then you can always designate any point of R2 with its coordinates, right? So it can be expressed as an ordered pair. So any point P belongs to R2 can be expressed uniquely as an ordered pair xy, where x and y are two real numbers, right? It is known to you that we can set up a coordinate system on R2 with respect to which, if we let O be the origin, then you can express any point by a coordinate by an ordered pair which is xy. Okay, fine. Okay, now on this R2 you can define addition, right? So define addition on R2 by this rule, that is P1 be a point, P2 be a point. Then their addition will have the coordinate system. Suppose P1 has coordinates x1 y1, P2 has x2 y2. Then the new point P1 plus P2 will have the coordinates x1 plus x2, y1 plus y2. Okay, just take addition component wise, that is component wise addition. This addition will be named as component wise addition. Okay, and you can check that with respect to this addition, R2 forms an abelian group. Okay, so this addition actually looks like this way. This is your origin, this is your, suppose in terms of your coordinate system, so it is your x-axis and it is your y-axis, and suppose you have a point, this is your P1 and suppose this is your P2. Okay, then how to get the addition of P1 and P2? Just take this parallelogram. So this point will be your P1 plus P2, right? Okay, so with respect to this addition, so R2 plus forms an abelian group. Okay, okay, now let capital L be a straight line in the plane R2 passes through the origin, passing through the origin O. So the origin has coordinates 0, 0, right? Then you can check that this L, so suppose this is your plane and suppose this is your straight line L. This is your origin. Now this L will form a subgroup first. And being an abelian group, we shall get that L will be normal. Okay. So to check that L be a subgroup, let us take 2 points. Suppose so let PQ belongs to L. Okay. So suppose PQ belongs to L, this L. Okay. Then, so what will be their addition? So pictorially speaking, if you see this picture, you will see that if P1 and P2 both are in the same line, then so is P1 plus P2, right? Because in that case, the area of the parallelogram will be 0. Okay, so that means P1, PQ and their resulting point with respect to the addition of P and Q, P plus Q will be in the same line where P and Q lies. Okay, so then PQ, P plus Q belongs to L. Okay, and if you take the negative of P and also minus P, then what is minus P? Suppose this is your P, so that means, so these are the coordinates. So what is minus P? Just take the same x coordinate and y coordinates in the left half plane here. So just take this and take this. This is your minus P, right? So minus P will be in the same line L. So minus P belongs to L. So that means, so this proves that L forms a subgroup, right? So given a plane, Euclidean plane R2, any line passing through the origin will be a subgroup. Okay. Okay, fine. So now uh, with respect to this subgroup, let us have a look at the right coset uh, or left coset, whatever it is. Okay, no matter, whatever it is. So let P be a point belongs to R2 and take the left coset of L in R2, that is P plus L. Okay, P plus L. Then what is the left coset? So how does it look like? What are the elements of P plus L? So if you take, so now since L be the line passing through the origin, so its equation can be written as, it must be of the form y equals to mx for some m belongs to R, right? Right? M greater than m not equal to 0. Right? So then what will be P plus L? So that means L will have the points of this form. So it is x mx for m belongs to R minus 0, right? Okay. Then what, and let the coordinates of P will be, suppose x0 y0. Then what is P plus L? So the P plus L will have the elements of this form. So x naught y naught plus, what are the elements of L? X mx, where m belongs to R minus 0. So that means for some m, yeah. So that means it is x naught plus x and it is y naught plus mx, where for some m belongs to R minus 0, right? Then this is x naught, yes. Then what can you say about this P plus L? So y equal to y naught plus mx. That means y naught plus mx minus mx naught plus mx naught. Okay. So that means this is equal to y minus y naught, and this is equal to m x minus x naught plus mx naught. right? Okay. Mm-hmm. I'm sorry. Sorry. So the new equation will be, so x, capital X is x naught plus x, that is x minus x naught equal to x. Yes. And capital Y equal to y naught plus mx. So that means y minus y naught equal to mx. Now what is x? X is x minus x naught. Yes. Yeah. So this gives you the equation of the line passing through. So this is the equation of the line passing through the point. What is the point? P. Passing through the point P. Okay. P equal to x naught, y naught. So what are the left cosets of L in R2? These are actually passing through the point this parallel to, yes, L. Okay. So this is the equation of the line passing through the point P parallel to L, because the this is the M. M is the slope of the line, right? Okay, fine. So that means, so if this is your L, suppose here it is your P, P is x naught, y naught, then this is your left coset, P plus L. Suppose you have, this is your Q, x dash, y dash, so then this will be your Q plus L. So the lines, so what are the left cosets of L in R2? These are all the lines passing through uh, points which are parallel to L. Okay. Okay. So therefore, so the factor group, so R2 slash L is consisting of precisely all the straight lines that are parallel to L. Okay, that are parallel to L. Okay, fine. Now I would like to stop by giving you a problem here. Uh, that let small a be an element of finite order in a group G, and capital N be a normal subgroup of G. Then prove that the order of the element n in the factor group G by n is a divisor of order of A. Okay. 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 Uh, describe the problem. Describe the quotient groups for the following cases. Number one, let E be the set of even integers in Z plus. Then what will be the quotient group of Z by E? Number two, Z in the group Q plus. Okay. Number three, R in the group of complex numbers with respect to addition. Number four, set of all rationals in R plus. Okay. Okay. And another good problem is that uh, yeah. Okay. What is S3 by A3? Another problem is that let ZG be the center of a group G where G by ZG is a cyclic group. Okay. Show that G is abelian. Okay. Okay. So this one I would like to stop here.
Thanks for watching. Please like, share and subscribe my channel.